Welcome, and in this video course we are looking at the CyberOps Associate version 1 course. This course is going to cover the skills and knowledge needed for successfully handling the tasks and duties, responsibilities of an associate level security analyst working at a security operations center. The goal of this video series is to help prepare learners for the Cisco 200-201 certification that's focusing on understanding the Cisco Cybersecurity Operation Fundamentals course known as CBROPS. Module 9 is all about the transport layer. So here we're looking at characteristics, session establishment, and reliability at layer 4. So we're going to be looking very specifically at our segment section, assuming it's TCP, or our segments if it is a UDP-based packet. Or, well, packets aren't really at layer 4, but segments are. So that package. So we're going to be talking about the transport layer characteristics. Essentially, the transport layer sits between the data portion and the communication portion. The data portion is going to be the application layer, presentation, the application, the session, those 765 layers. Transport sits between that and the internet data link and the physical layer. Again, the two main protocols are TCP and UDP. TCP is connection oriented, UDP is connection list oriented. So let's drill down into that. Basically, the goal with layer 4, it's about being able to transport data but track individual conversations. Let's say you have a browser window open. In reality, each window is going to be a separate session. So each application window may actually have 3 different streams out to a website, for example. Well, this section actually allows for the communication between the web browser window and your web resource. That way, when the web resource returns, it's not so much going back to a different window, but only the actual application window that requested the information. It is basically the responsibility of the transport layer to maintain and track all conversations. In the diagram, you'll see that we have one computer. They may have, 6 different things going on, but the application, normally a web browser, is going to be tracking each one of them. If not the application, then the actual underlying communication suite, because the transport layer is the responsible party for tracking. So keep in mind that layer 4 sits on top of layer 3. Layer 3 is our packets, but only so much data can be put into each individual packet. So what ends up happening is at layer 4 we chunk or segment the data into manageable pieces. That way they can be addressed and sent either from the source to the destination or as a return process, but in a manageable manner. So when we say individual conversation and tracking, that also includes that segmentation. Again, piecing the data into manageable chunks is part of that segmentation. That meant as it is sent through the network, it also has to be reassembled. So that happens at this layer as well. Each layer is tracked, and each group of data or each package of data that is sent has to be able to be re-put back together or put back together. The transport layer is divided in the data into smaller blocks, again segments or datagrams. They're easier to transport and manage. Just like in the previous layers, we're also going to be adding header information. Whether it's TCP or UDP, you will get a layer 4 header. The header information is used on the receiving end to basically reassemble everything. So it's not just about the individual tracking, it's all of the smaller portions of that. The transport layer will ensure that even with multiple applications running, only the correct application, the correct window in the application, will receive the correct data. So identifying the application is going to be based off of service ports. Normally, things like port 110 is going to be electronic or email. Port 80 or port 443 might be a web page. Internet chat is normally port 531. These are ways to actually separate the logical flow of traffic based off of the category of the type of traffic. If it is sending email, that might be SMTP port 25. If we are talking about DNS, that might be port 53, and so forth. So identifying the application is based off of the destination port number. And again, that's the way the application is used to identify itself. It uses port numbers. Remember, because you can handle multiple conversations like email and web page and internet chat all at the same time, there has to be some type of conversation multiplexing. Basically, this is going to be taking the ability to have some types of data across the network, whether it's streaming, whether it's traffic, whether it is online video chat, and putting it all together so that it can process correctly. So again, the segmentation will allow the conversations to multiplex, meaning multiple applications can use the network at the exact same time, and this is done through the segmentation portion. The transport layer, again, two main protocols, TCP and UDP. Some protocols can either be either or, while some protocols can be both. DNS is actually both TCP and UDP, while many protocols only select or opt for one of these connections to communicate. Several of these only opt for one type of transport communication channel, either TCP or UDP. Again, TCP is used for reliable, guaranteed traffic. UDP is best effort. TCP will be reliable, full-featured. It ensures that all data is sent and received, and if it isn't, then it resends it. TCP transport, basically, it's going to be source to the destination, and if the destination doesn't receive all of it, then it redoes the transmission again until the destination gets all portions of the conversation. In contrast, UDP does not do that. TCP provides reliability. It does numbering and tracking of each data segment. It will also have to acknowledge each data segment. Any segment that is not acknowledged will be retransmitted, and there is a sequence number that puts them back together in the right way. Remember that if we're using TCP, the data is broken up into data groups known as segments. In order to maintain the state of a conversation, TCP must be able to track, and it has to do that first by establishing a connection. And they do this via a process known as the three-way handshake. Remember, TCP is known as the connection-oriented protocol, meaning it will establish a connection, and that way it can verify all data sent is actually received, and then, if necessary, retransmission. TCP is stateful, meaning it will keep track of the communication sessions. Here is the header of a TCP packet. You'll notice there's a source and destination port, a sequence number, an acknowledgement number, as well as other data. Remember, this is stateful, meaning that the session establishment and ends with a session termination. TCP header is going to add 20 bytes or 160 bits of overhead to the overall data group. Each one of those categories is like source and destination port, sequence number, acknowledgement number are clearly defined here. Source number is again used for reassembly. Acknowledgement number is indicating that they receive and are ready for the next packet or next segment. Header length is a 4-bit field known as the data offset, Reserved is again reserved for future use. There's a control bit, a window size, a checksum, and some form of priority, urgent, essentially. In contrast, we have UDP. UDP is very simple. It is best effort, connection list oriented. It doesn't provide reliability or flow control, but it has a much smaller header. The sender and the receiver UDP process don't have to manage the reliability or the flow. Basically, you send the packet. If you get it, great. If you don't, oh well. There is no specific recovery process. Again, UDP is connectionless because there is no reliability built into this. UDP is known as a stateless protocol because no tracking information is actually maintained. UDP is that will divide the data into datagrams, and oftentimes these datagrams can also be referred to as a segment, or sometimes you can refer to them as a datagram. It really just depends on who you're conversating with, because both of these can go. If you're looking at TCP, TCP is only going to be a segment. UDP is either a datagram or a segment based off of the individual you're talking with. So again, when we're looking at TCP and UDP, TCP connection oriented, UDP connectionless oriented. TCP guaranteed delivery, UDP not. So why would we want UDP? Why would we want best effort? Well, you have to think that overhead costs delay, causes time. So what ends up happening is if you have something like real-time traffic, voice, video, for example, and there is a delay in it, then that can cause some synchronization issues. That is why UDP is not so much used for guaranteed delivery. It's going to be best effort because it's about speed of delivery. One of the big takeaways with UDP is going to be the simplified header. You'll notice this is way smaller. UDP basically adds 64 bits or 8 bytes to the actual overall datagram. 16 bits for the source and destination port, 16 bits for the length, 16 bits for the checksum. That's it. Very simplified header. Remember that source and destination ports are the 16-bit field used for identifying source and destination applications. We normally look at destination port, like port 80, that goes to a web server, but we also have a source port that normally is randomly generated. So another core concept here is the socket pair. Basically, the source and destination ports are placed within the segment. The segments are then encapsulated with the packets. The IP and port number combined make the socket pair. That way you can actually see source, port, and IP address, destination IP, and destination port. That way it is going to be a guaranteed from source to destination and hopefully a return process. The socket pair, again, we look at the ports and the addresses, them combined make the pair. Sometimes you will actually hear socket pair referred to as the source and destination ports together, combined. This is also true. This is not looking at the communication back and forth. This is looking at just the layer 4 communication back and forth. So if you have a source and destination port, them grouped together can also be known as the socket pair. Normally using the source port to identify the source machine, and then the destination is actually going to a specific web resource or a specific network-based resource. So a client socket with 1099 will represent the source port, might be the IP address colon the address. This is how normal socket pairs are normally written. You will see the IP colon the actual port number. That is what I meant by the socket pair. You'll see them grouped like that. And this is not a well-known port, so realistically this might be a random source, and this might be the destination. So now let's go and let's dive into the establishment. Since we talked about TCP actually having to require a established session, let's talk about the TCP establishment. Alright, so essentially each application or each process on a server is going to be configured to use one specific port. These are normally called bindings. So if you have a web server, you may bind the IP address with port 80 or port 443. And again, that meant anything coming in on that port is going to access that resource or that application. So understanding the port numbers, like port 80, you know that's basic HTTP traffic. Port TCP 443 is going to be HTTPS based traffic. That essentially means as the information comes in, the device is going to accept the request on that port and then forward it to that appropriate application. Any incoming client request addressed to the correct socket will be accepted. The IP colon the port number. And then the data will be then passed to the application. There can be many ports, there can be many communication. But again, when we're looking at this is where the socket set or the socket pair come into play. If we have 10 requests coming in and they're all requesting destination port 443, and each one of them have a different source port, then that allows for 10 different applications, 10 different sessions to the same application. Because there might be 10 different computers accessing the same web server. Here's an example. We may have one server that hosts multiple resources. And so if they are the same destination port, and it's a different randomized source port, then each one will still be allowed to communicate. So they're requesting destination port, again, port 80, port 25, that's going to be the key application that's running on the server. Then the source port is normally a dynamic or randomly generated source port that will be used to uniquely identify the individual. The response destination port is going to be the response. So on the destination, here in that case the server is going to do the destination port at reverse. It will then take whatever source port was originally there, and that's going to become the destination port. And then the source port from the server perspective will be the port 80 or port 443 or port 25 or whatever the original destination port is. It basically flips them so that communication can go back to the original source. Again, the source port would then become the original destination port. That will become the new source port. So we talked about the establishment of a TCP session. This is known as a three-way handshake. So part of this process will start with the source, the sender. They'll send a sync request. The destination will have a sync receive. The requester, computer A in this example, will have a sync number randomly generated, let's just say 100. And what ends up happening is the sync received will then generate a new sequence number, and then the acknowledgement will be 1 plus the original sync number. And they will respond with a sync ACK or sync acknowledgement. In that case, computer B will then receive the sync acknowledgement. The third step will be the establishment, and that means it will respond with a sequence number matching the sync ACK. The acknowledgement number will be 1 plus the sync ACKs number, and then there will be a acknowledgement. So let's go ahead, let's look at these numbers. So this is a randomly generated number, and that will directly correlate to the acknowledgement number. That will be 1 plus that guy. And this acknowledgement number here is 1 plus the sequence number. But it's also equally important to point out that this acknowledgement number will be equal to this sequence number. And then there is also a termination process. That original three-way handshake was to actually start the session. This would be the way to terminate the session. And basically we'll be sending a SYN flag or a FIN flag to terminate it. This basically is a control flag in the segment header that says let's terminate it. To each one-way TCP session or two-way handshake, which will consist of a FIN segment and a acknowledgement that is used. So when we're ready, we'll send a SYN flag. The destination will have the FIN received. Then the computer B, in this case, will then send an acknowledgement acknowledging that it was terminated. What will end up happening is the destination, computer B, will also send its own FIN, and the original source will have to receive it. So one side sends a SYN, or one side will send a FIN, and we'll get an acknowledgement. So this one terminates it for computer A. This one will terminate it for computer B. Both sides will have to send a FIN. Both sides will have to have an acknowledgement acknowledging the receipt of the SYN. So this is the three-way handshake analysis, essentially. You can establish the connection between the source and destination, and you can look at these sequence numbers. The big thing that we've been looking at are these control bytes. Normally there are 6 different control bytes: urgent, acknowledgement, push, reset, sync, or FIN. So FIN is going to be no more data, sync is going to be synchronizing the sequence number, the reset will be reset the connection, the push function is to be push data, acknowledgement will be the acknowledgement, and then urgent will be urgent. In the reading there is a video walking through this again. We also have an additional lab. So with that said, we have our last major section, which is the transport layer, looking at reliability. Again, TCP is reliable, guaranteed delivery in a specific order. Because there are times when the segment may not arrive in the correct order, so there has to be a way to put them back in order. And for the segments that didn't actually arrive, there has to be some way to resend just the packages that were not delivered. We do that through sequence numbers and acknowledgements. So during the original session, an initial sequence number is set. This will represent the starting value of the bytes that are transmitted. Each packet will have sequence numbers based off of that. This data will basically track each individual package as it goes between source and destination, thus guaranteeing delivery. There is also a breakdown of the segments. We said that layer 4 deals with taking the large chunks of data and segmenting it. Well, there is an order to that. If the order is received out of order on the destination side, the segments are actually numbered so that they can be reordered. And again, in our chapter reading, there is a review of that as well. Essentially, TCP provides a sequence number and an acknowledgement number for transmission and for reordering. Remember that TCP will use an acknowledgement number to acknowledge the receipt of received data. Here's an example of reliability and data loss as well as retransmission. So we'll get like a segment 1 and 2. We may respond with an acknowledgement based off of the 2 items that were received. Then it should say we didn't receive 3 and 4, so it may actually have to reissue those. You'll notice an acknowledgement after the segments that were actually received. Host operating systems normally will employ an optional stack called the SAC, the selective acknowledgement. That way it can actually say what it received and what it did not receive. That way you're not having to resend large chunks of segment that you already received. If you did a window of, let's say, 5 segments, then every 5 segments you should get an acknowledgement. If you got segment 1, segment 2, and segment 5, but you didn't get 3 and 4, you should be able to say the selective acknowledgement is 1, 2, and 5. The ACK would then be 3. That way it would know which ones to retransmit without having to retransmit segments that were actually already received, but because of the window size is not being acknowledged. Again, window size is going to be how many sets or how many segments are sent per acknowledgement. Is it 1 segment? Is it 5 segments? Or is it more? And again, that's called the window size. The reading has an additional video looking at our retransmission. So we just talked about flow control. We just specifically talked about window size. And again, the flow control is the mechanism about how much data can be sent and received in an orderly fashion. Also, how much data can be sent per acknowledgement. That's going to be the window size. Here we have a window size agreeing, and from there we can build off of that. The window size essentially allows you to set how much data can be sent and received at one point. So the destination will not wait for the bytes for the window size to be received before replying the acknowledgement. That's another big thing. Basically, devices today will use a sliding windows protocol for the receiver to send an acknowledgement. So after every 2 segments are received, basically allowing the slider to be modified. That way we lose less overhead. The advantage of a sliding window is that allows the sender to continuously transmit segments as long as the receiver is acknowledging the previous segments. Essentially, the goal here is to think about that we're not going to be stopping sending data and waiting. We're going to keep sending, and we'll wait. We're going to just kind of keep sending the data, and while we're sending that data, we may put on pause some of the older segments waiting for that acknowledgement. It's still sending the new segments, but it still will wait for the acknowledgement. And if no acknowledgement actually is sent, then it will request a retransmission of that item. There's also a maximum segment size, an MSS. Normally that is going to be the maximum data size of around 1400 bytes. Remember that the MSS size does not include the actual header. This is just basically the agreed upon size during the three-way handshake. So what we end up doing is we look at the entire data packet, we look at the section for TCP, we look at the MTU, and from there we decide what the size is going to be. Normally it's about 1460 bytes. Again, the default MTU is 1500 bytes, but you can subtract some of the header information, like the 20 bytes for the TCP header. That would be 20. So that will leave the default size of 1460. IP header of 20, TCP header of 20, that's 40. 1500 bytes minus 40 is 1460. When congestion occurs, basically, this is where the sliding and the acknowledgements really come into play. When congestion occurs, it will retransmit data packets and it will discard overloaded routers. When the routers are overloaded, it'll start dropping packets, meaning those packets won't be delivered. Those packets not delivered will end up just being retransmitted, which then could result in more congestion. By determining the best rate that the segments can be sent without acknowledgements, the source can assume a certain level of network congestion, and then the sliding window can come into play. So whenever there is congestion, retransmission, or loss of TCP segments can trigger this negotiation of what should occur from the source's perspective. If the retransmission is not properly controlled, however, transmission can really kick in and make things worse. Here is the example of us being able to transmit 4 data segments, and then we get an acknowledgement for 2, then we retransmit 2 and 3, and so forth. We have lots of labs examining the transmission and the Threeway handshake process, so do keep that in mind. We also have a lab exploring entry-level InMap. This is a network reconnaissance tool that we're going to be looking at. So that actually is all for this chapter. We looked at the transport layer more in depth. We looked at TCP and UDP in depth, the overhead, the header information, stuff like that. We looked at TCP control flags, urgent acknowledgement, push, reset, sync, and our thin. We also looked at our ACK versus our selected ACK, and we looked at flow control and window size. And that is it for this chapter. If you have any questions or anything, please feel free to reach out. Again, with this material, being able to ask questions and discuss some of the topics in the lecture help build long-term retention, so do not be afraid to communicate with this topic. Again, I'm here if you need anything. Thank you.